Now, sometimes you'll be asked to sketch something and you'll need to find some information in order to complete your sketch. Other times it can be easier to actually make a sketch and then find the information from the sketch. So always be prepared to think both ways. Now, I can see here that if I've got to find zeros and discontinuities in y dash, that's in the first derivative for this curve, then if I can sketch the curve and just spot any sharp corners, vertical bits, or discontinuities, then I'm going to be there. It also would make sense to confirm my suspicions from my graph by actually finding the equation of y dash and just checking that both things match up. Let's throw our algebra at it first and differentiate it. Now, we can't differentiate it with that surd there, so we need to rewrite it like this first. Then we can differentiate that and say y dash is equal to, we bring our third out the front, and then we rewrite the x and we drop our power down by 1. So subtracting 1 from a third gives us minus 2/3. Now, you can keep it like that, it's totally fine, but for it to make more meaning, it might be handy to rewrite it in a more familiar form. Now, we've got the 1 on the top and the 3 on the bottom of a fraction, but also this negative power here means that this whole section, x to the power of 2/3, comes down the bottom here. And x to the power of 2/3 is actually x squared, all to the cubed root. So I can rewrite it like that if I want to. Now, why would I want to do that? Well, I can see where y dash is undefined straight away. So I can say y dash is going to be undefined at x equals 0. Now, how did I get that? Well, because I've got a fraction here. The denominator can't be 0, and it's going to be if x squared is 0. In other words, if x is 0. So I've straight away found that it's undefined there. Now, what about finding the 0 of y dash? What does that really mean? Well, it means that if I was to sketch this, would it ever equal 0? Now, how would I go about sketching this, and how do I go about finding the zeros of the discontinuity? Well, let's think about what the zeros of y dash really are. Aren't they the stationary points? They're the times that y dash is equal to 0. Okay, so in other words, they're the flight spots in the original curve. Now, at this point, I think it might be handy just to go ahead and sketch the curve. Now, if you're not sure how to sketch this curve, the easiest way to sketch it is to say that this is the same thing as y cubed equal to x. Now, what I just did there is I cubed this side and I cubed that side. Now, cubing both sides might change the nature of it a little bit, but it shows me what to do. Now, you guys know how to draw y equals x cubed. That looks like this, and it's got a little flat spot in the middle, and I can label that y equals x cubed. So what does x equals y cubed look like? Well, it's the inverse function, isn't it? Because it's just swapped the x's and the y's of these two. So if I was to graph the line y equals x, and I'll do it as a dotted line here, then all we need to do is reason that x equals y cubed, or in fact this curve here, is just the reflection around that line. It's heading off like that, and it's going to have a vertical section here, and then head off like that. Okay, now rubbing out the original line, we could do that, or we could just say this is y equals the cube root of x. What can we see straight away in terms of undifferentiable sections? Well, I can see it's going to have a vertical section right here. And it's got a vertical section just because y equals x cubed has a horizontal section. So if we've graphed its inverse, or its reflection around the line y equals x, then we now have a vertical section of the curve. So we can see that y dash, or in other words, the gradient or the first derivative, is not going to be defined there. Now, we found that algebraically, and we can see that it lines up with what we can see graphically as well. So are there any zeros in y dash? Well, does this curve have any flat spots? It doesn't, does it? And why is that? Well, it's because y dash can never equal 0. Okay, because it's a fraction with a 1 on the top. It will never be 0. Therefore, y dash has no zeros. So we've answered our question. It has no zeros, and it's undefined only at that point. And we considered it graphically and algebraically, and everything seemed to match up, so we can be pretty certain of our two results here. Whenever you've set out your working and you feel like you've made a bit of a mess, I do this quite often, one strategy is you can write out your answer neatly at the end, or you can even just put a box around the most important parts, so it's really easy for an examiner to spot your answer. Okay, this last one is a little bit more tricky because we need to find the zeros and discontinuities of y dash, or the first derivative, for this curve and then sketch it. But we've got a curve here that actually doesn't have any vertical asymptotes and it doesn't have any discontinuities in it itself. So the only reason that it could potentially have discontinuities in y dash is if it's got vertical sections or sharp points, and we need to look out for both of those and know how to find them. Now, we probably haven't sketched this curve before, so it's not one we're familiar with. So we're going to need to throw all of our tools at it. Now, I said before it's not going to have any vertical asymptotes in it. How did I know that? Well, I've glanced at it and just thought about what this means. I can write that out as x squared all in a cubed root. And I can see that I can take any value of x and square it and then find the cubed root of it, whether it's positive or negative. So x can be anything, and the domain is going to be all real x. So we're not going to have any discontinuities in y itself, but we might have some in y dash. All right, so first let's go ahead and differentiate this thing. So y dash is equal to, we need to bring the 2/3 out front, and then rewrite the x and drop our power down by 1. Now, we can write that a couple of different ways. We could have a big fraction with a 2 on the top and the 3 on the bottom for the 2/3, but this is bringing the x to the third down onto the denominator, isn't it? And that can be written as the cubed root of x. So I can see now that y dash can't equal 0 because this fraction here can never equal 0 because it's got a 2 on the top, and you can't do 2 divided by anything to get 0. So therefore, there are no zeros in y dash, and you should be thinking to yourself, what does that mean? Well, it means there's no stationary points. There's no flat spots in this curve. Okay, what about looking for discontinuities? What can y dash not be? Well, this is a fraction, so that means that the denominator can't be 0. So let's write down our thinking here, but 3 times the cubed root of x can't be 0, therefore x can't be 0. So if x is 0, what's going to happen? We would have a discontinuity in y dash. So therefore, let's say that there is a discontinuity in y dash, which is the first derivative or the gradient of the curve, when x equals 0. Okay, how are we going to go about graphing this thing? Well, we've got our curve sketching menu. Let's consider. Prepare it, no real point. We've thought about how it might look. The domain, we've considered that it's all real x. Intercepts, if we let x equal 0, what will y be? It'll be 0, won't it? Okay, so we can go ahead and graph that. Let's just go get a pen. It must go through the origin. Okay. Now, what about oddness and evenness of this curve? I mean, if we write it like this, perhaps it helps us to see. That big x squared really gives it away, doesn't it? That no matter what x is, if it's negative and we square it, we're going to get the exact same answer for y as if we had the positive counterpart of that same x value. So clearly this is an even function, and that means that whatever's happening over here, we can just repeat over there. It sort of halves our workload, if you like. Now we need to work out what's causing this discontinuity. Is it a sharp corner? Is it a vertical section? Could it be both? Now, an easy thing to do is just to consider what's happening to your curve and what's happening to your gradient at different values of x. Now let's just use nice friendly numbers. Let's start from 0 and just use nice integers, and then consider as we approach infinity, so as we're approaching infinity, what's happening to y, what's happening to y dash, because we have a formula for that. Now if we know what's happening over here, we can just reflect it over to this side. So if we square each number and then take the cubed root of it, the first couple are really easy. Here we're going to have the cubed root of 4, the cubed root of 9, the cubed root of 16, and we can quickly and easily put those into a calculator to figure out rough values for what we're going to have. So this one we've got, that's roughly 2.08, 4 cubed root is roughly 1.59. So we can see that it's going up and then it's sort of starting to level out a little bit. 16 cubed root is 2.52 or so. So as we're heading towards infinity, we've got the cubed root of infinity squared. That's a little hard to think through. But if we look at what's happening with our gradients, as x gets really, really big, what's y dash going to do? Well, it's got this formula. As we have a giant number here, and we take the cubed root of it, it's still going to be massive, right? And so if we've got 2 over 3 lots of a huge number, it's going to tend towards 0. So as x approaches infinity, y dash, which is the steepness of the curve, is approaching 0, so that tells us it's flattening out. Now it's never going to get fully flat because we can see that there's no zeros in y dash, but it's getting flatter and flatter. So it looks like it's got some sort of a curve that's doing this sort of thing. And that is backed up by the y values that we had. They were getting bigger, but they weren't adding so much each time. The fact that we couldn't really pin down this didn't matter, because looking at what y dash was actually easier there for seeing the shape. So we've got something like this, and we've already seen that we've got even symmetry, so I'm thinking that the other side goes out roughly the same. Okay, well, they don't look very symmetrical, but you can see what I'm trying to do there. So it seems that we do in fact have a sharp point, and we may also have a vertical section. Do we need to check? Well, it wouldn't hurt, because it'll make our graph that little bit more accurate and check that we've drawn things right. So how are we going to check that? Well, let's consider as x approaches 0 from above. Now, we've seen this notation before. The little plus there means we're approaching 0 from above, so we're getting tinier and tinier and tinier numbers, but they are positive. So in other words, we're heading this way towards the origin. Now, as we do that, what is y dash heading towards? Well, we've got a formula here for y dash. As x gets really, really close to 0, but isn't actually 0, if we take the cubed root of a really tiny number, now take your calculator out right now, and actually just put in a tiny number like, I don't know, let's just go 1/100th, that's pretty small, 0.01, let's take the cubed root of it, and then let's go to divided by that number. What do we get? Well, what we get is a really large number. Y is approaching infinity. Now, a steepness of infinity is very steep, right? So we're seeing that it's going to get steeper and steeper and steeper. Now, eventually it's going to get so steep that it's going to be undefined. And we know that because we've already seen that there's a discontinuity in y dash there. So in fact, yes, it's going towards a sharp corner and a vertical section in the graph at the same time. And we've sketched our curve. We've found that there's no zeros in y dash, and we found that there was a discontinuity in y dash when x equals 0.